Okay, I'm just going to make a quick video to explain the thought process to approach how to work out the force required to lift an object. So first let's look at a diagram we've drawn. So maybe if you're giving in a description or something, the best thing to do to start with is always draw a diagram. So we've got one here. So we've got an object that's being lifted up, and we've got drawn on there, we've got the weight force acting downwards. And what we're saying is that this object, in addition to being lifted, is also being accelerated. So that's going to require force to accelerate it as well as to counteract the weight force. So what we say is that obviously we're going to assume that the mass of the object stays constant. So Newton's second law obviously is that the force is proportional to the rate of change of momentum. Obviously if we assume mass is the same, we can say force is mass times acceleration. So obviously the key thing to note is that in this equation here, the F, the force, it's not just force, it's the resultant force, okay? So that's just the force that's being used to accelerate it. That doesn't take into account forces to balance weight, for example. So what we're interested in this case is the total force. And that's going to be, in this case, just as before, so we've got MA, and we're also going to have to add on there mg, because we're going to have to overcome the weight force of the object too. So, for instance, if we had a question where, I don't know, the acceleration was 3 meters per second squared, the mass was 2 kilograms. Obviously, g is going to be usual, so it's going to be 9.81 newtons per kilogram, or whatever unit you decide to give it. Doesn't matter too much. So in this case, the force total is going to be equal to, we've got two lots of m, so I'm going to factorize this first, just to make it, so I'm going to reduce the number of numbers we've got going on there. So I've just factorized that. So then we're going to calculate m was 2, a was 3, and obviously g is 9.81, which is, if I'm not mistaken, 2 times 12.81, which is going to be 25.6. Actually, no, that's ridiculous. Why would I give 3 significant figures when the information in the question only had 1? So we're going to round that up there to 26 newtons. So that 26 newtons includes the resultant force needed to cause that acceleration, and also to counteract the weight force of it. Okay, so what if our object is not moving up, it's moving down? Because a lot of people intuitively think, well, if it's going down, you don't need to be supplying any force upwards. But, well, quite frankly, I don't want to be in a lift where that's the case, because I don't want to be free-falling down the side of a 90-story building. I'd like to be in a nice controlled descent. You're obviously going to need to accelerate at some point, but I certainly don't want it to be accelerating at the rate of gravity. So let's have a look at this scenario here. So again, we've got a diagram. So we're still supplying a force up, as you can see in the diagram. Obviously, this time we're accelerating downward. Okay, so let's have, again, using our friend Isaac Newton's equation. So we've got the resultant force on it is equal to mass times acceleration, because again, we're going to assume that the mass is constant, so we can simplify it to this. And in this case, that's going to be 2, we said it was 2, and the acceleration is 3, so the resultant force is 6 newtons. So that's the force required to cause that acceleration. Now in this case, the total's 4, so let's have a look at the force downwards. Okay, so the force downwards is equal to 2g, which is what? 19.6. I don't need to go into more significant figures than that. That would be ridiculous. So you can see that that's much bigger than the resultant force that you need. So F must be equal to the difference between those. So F is going to be this 19.6 blah 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 minus the resultant force you need, because it has to supply a difference to prevent it accelerating more. So that's going to be 13.6, but obviously the information in the question only gave us one sig fig, so it would be ridiculous to give 3 sig figs in an answer. So I'm just going to give 2. So that would be 14 newtons, which compared to the last example was quite a bit smaller. But again, it's still like a reasonable force you have to apply.